Assalamualaikum and welcome to Linear Control System lecture. This lecture is a continuation from the last section in Time Response Analysis, Introduction to Second Order System. Recap, the prototype of a second order system is given by Gs equals to omega n square over s square plus 2 zeta omega ns plus omega n square. System response for a unit step input is given by this equation where Cs is the output, Rs is the input. Scope of discussion on the left-hand side of the S-plane since the system will be unstable on the right-hand side of the S-plane. The oscillation keeps on growing and does not decay at all. For a stable system, if the poles are located on the imaginary axis, the value of zeta is 0. Thus, the system response is undamped. If the poles located on the real axis, the value of zeta is greater than 1. Thus, the system response is overdamped. If the poles located on a single point on the real axis, the value of zeta is 1. Thus, the system response is critically damped. Finally, when the poles are located in between the imaginary and real axis, the value of zeta is greater than 0 and less than 1. Thus, the system response is underdamped. A plot of this response appears in the figure for various values of zeta, plotted along a time axis normalized to the natural frequency. So we now see the relationship between the value of zeta and the type of response obtained. The lower the value of zeta, the more oscillatory the response. The natural response is a time axis scale factor and does not affect the nature of the response other than to scale it in time. We have defined two parameters associated with second-order systems, zeta and omega n. Other parameters associated with the underdamped response are rise time, peak time, percent overshoot, and settling time. Notice that the definitions for settling time and rise time are basically the same as the definitions for the first order response. All definitions are also valid for systems of order higher than 2, although analytical expression for these parameters cannot be found unless the response of the higher order system can be approximated as a second order system, which we will discuss later. Rise time, peak time, and settling time yield information about the speed of the transient response. This information can help a designer determine if the speed and the nature of the response do or do not degrade the performance of the system. For example, passenger comfort depends in part on the suspension system of a car and the number of oscillations it goes through after hitting a bump. We now evaluate peak time, percentage overshoot, and settling time as functions of zeta and omega n. Notice that the settling time and peak time is related to the pole location on the S-plane. The settling time related to sigma d, which is the magnitude of the real part of the pole and is the exponential damping frequency, whereas the peak time is a function of omega d, which is the imaginary part of the pole and is called the damped frequency of the oscillation. Settling time is inversely proportional to the real part of the pole. Since vertical lines on the S-plane are lines of constant real value, there are also lines of constant settling time. We can see step responses as the poles are moved in a vertical direction, keeping the real part the same. As the poles move in a vertical direction, the frequency increases, but the envelope remains the same since the real part of the pole is not changing. Since all curves fit under the same exponential decay curve, the settling time is virtually the same for all waveforms. Note that as overshoot increases, the rise time decreases. Similarly, peak time is inversely proportional to the imaginary part of the pole. Since horizontal lines are on the S-plane are lines of constant imaginary value, they are also lines of constant peak time. Let us move the poles to the right or left. Since the imaginary part is now constant, movement of the poles yields the responses where the frequency is constant over the range of variation of the real part. As the poles move to the left, the response damps out more rapidly, while the frequency remains the same. Notice that the peak time is the same for all waveforms because the imaginary part remains the same. Finally, since zeta equals to cos theta, radial lines are lines of constant zeta. Since percent overshoot is only a function of zeta, radial lines are thus lines of constant percent overshoot. Moving the poles along a constant radial line will not change the percent overshoot, as the percentage overshoot is a function of zeta. Notice also that the responses looks exactly alike except for their speed. The farther the poles are from the origin, the more rapid the response. That's all the information you need to know regarding the second order system. Next, I'll show you the effect of additional poles and zeros to the system response. If you have any questions, please leave me a message or comment and I'll try to get back to you. Thanks for watching.